Hey everyone, and welcome. We're surrounded by liquids all day, every day. Water, coffee, you name it. But have you ever really stopped to think about the invisible forces that make them, well, do what they do? Today, we're going to pull back the curtain and uncover the secret rules that explain everything, from why a puddle vanishes to how a tiny insect can literally walk on water.
So, let's kick things off with a little mystery. Picture this. You see a puddle of rain on the sidewalk. It's not a hot day, not particularly sunny, but a few hours later, it's just gone. Poof. Where did it go? The answer to that simple question is the key that unlocks the entire secret life of liquids.
All right, so to crack the case of the disappearing puddle, we got to take one quick step back and just remember what makes a liquid, well, a liquid. What makes this state of matter so unique?
Liquids are kind of like the rebels of the states of matter, right? They flow and take the shape of whatever you put them in, kind of like a gas, but they have a fixed volume, like a solid. And it's all because their particles, their tiny little molecules, are packed in there pretty tight, but they're not locked in place. They can still slide and tumble past one another. And that freedom to move, that's everything. So if all these particles are free to move around, what stops a glass of water from just flying apart and turning into a gas right in front of our eyes? Turns out there's this kind of secret molecular glue holding it all together. It's an invisible force that dictates pretty much every single thing a liquid does. And this glue has a name: Intermolecular Forces, or just IMFs. Now, it's super important to get this right. These aren't the super strong bonds inside a water molecule holding the hydrogens to the oxygen. Nope. These are the much weaker but absolutely crucial attractions between neighboring molecules that keep them huddled together as a liquid. And this molecular glue comes in a few different flavors. You've got forces between molecules that act like tiny little magnets with a permanent positive and negative end. Then you have this weaker, sort of temporary stickiness that all molecules have. But the real superstar, especially for something like water, is hydrogen bonding. Think of it as a supercharged version of the magnet-like forces. It is incredibly strong and makes water act in all sorts of special ways. So here's the bottom line. The type of molecule you have determines how strong its glue is. Polar molecules, the ones that are like tiny magnets, have these stronger attractions. But nonpolar molecules, they're more balanced, so they rely on much, much weaker temporary forces. And believe me, this difference in glue strength is a huge deal, as you're about to see. Okay, let's get back to our puddle. The process that's making it vanish is called evaporation, and you can think of it as a constant battle going on at the surface, a battle between a molecule's energy trying to escape and that molecular glue trying to hold it back. So, what is evaporation? Simply put, it's a liquid turning into a gas or a vapor. But here are the two crucial things to remember. It only happens at the surface of the liquid, and it can happen at any temperature. You don't need to be boiling water for it to evaporate. Just imagine all the little molecules in our puddle constantly jiggling and bumping around. A few of the ones right at the top, the really energetic ones, get just enough of a kick to break free from the pull of their neighbors and leap out into the air. Now sure, this happens faster if the puddle is spread out or if it's warmer, but the number one factor? It's the strength of the glue itself. A liquid with weaker forces, like gasoline, evaporates way, way faster than water. And this brings us to our first big, unbreakable rule. Weaker molecular glue means faster evaporation. It's as simple as that. It's why a gasoline spill seems to just vanish in minutes, while our water puddle takes its sweet time over a few hours. The molecular glue in gasoline is just, well, it's a lot weaker than the super strong hydrogen bonds in water. Now here's a really cool side effect. Literally. Think about it. If only the most energetic, hottest molecules are the ones escaping, what does that do to the ones left behind? Well, the average energy goes down, which means the liquid that's left over actually gets colder. This is exactly why sweating cools you down. As the sweat evaporates, it pulls heat energy away from your skin. Pretty neat, right? Okay, so that's evaporation. Now let's dial up the drama and talk about boiling. While evaporation is a quiet process that happens only at the surface, boiling is a full-blown chaotic event that happens throughout the entire liquid. And it's all about pressure. A liquid's boiling point isn't just some magic number.
It's a specific temperature where the molecules inside the liquid are pushing outwards with enough force, we call it vapor pressure, to overcome the weight of the entire atmosphere that's pushing down on it. It's like a tug of war, and at the boiling point, the liquid finally wins. And of course, our molecular glue is the star of the show here too. If the forces holding the molecules together are really strong, they're held down tight. It takes a ton more energy, a higher temperature, to get them moving fast enough to build up that escape pressure. So stronger IMFs mean a higher boiling point. It's why water with those powerful hydrogen bonds doesn't boil until it hits a pretty high 100 degrees Celsius.
But check this out. What if you change the pressure pushing down? If you go to the top of Mount Everest, the air is really thin, so the atmospheric pressure is way lower. This means water doesn't have to fight as hard to boil. And get this, it boils at just 69 degrees Celsius up there. That's about 156 Fahrenheit. You could literally dip your finger in it without getting a serious burn. It also makes it almost impossible to properly cook things like pasta or rice.
That same molecular glue also controls how liquids, behave in the real world. Things like how easily they pour, or that weird, almost invisible skin that forms on their surface. I mean, just picture it in your head right now. Think about pouring a jar of honey, and then pouring a glass of water. The difference couldn't be more obvious, right? Honey just oozes out slowly, while water flows freely. And that property comes directly from the strength of those intermolecular forces. This resistance to flow has a name. It's called viscosity. The molecules in a thick liquid like honey have really strong IMFs, so they cling to each other and refuse to get out of the way. They just don't want to let go. So the rule is simple. Stronger intermolecular forces means higher viscosity. And what about that skin on water? The thing that lets little water strider insects skate across a pond? That's surface tension. See, a molecule in the middle of the liquid gets pulled equally in all directions by its neighbors. But a molecule at the surface, it only gets pulled down and sideways. There's no pull from above. This net inward pull creates this tight, elastic-like layer at the surface. And you probably guessed it, stronger IMFs create a higher, tighter surface tension. So we've seen how stronger forces totally change how a liquid behaves. But what if we could actually put a number on the strength of that molecular glue? Well, we can. It's a bit of a mouthful, but it's called the molar heat of vaporization. The easiest way to think about this is that it's the energy price you have to pay to break all of that molecular glue and turn a set amount of liquid into a gas. A higher price means stronger glue. Simple as that. And this chart just says it all. I mean, just look at that. Look at the enormous amount of energy it costs to vaporize water compared to other liquids like ammonia or hydrogen chloride. It's not even close. This is the hard data, the visual proof of just how insanely powerful water's hydrogen bonds really are. It's why it takes so much time and energy to boil a simple pot of water on your stove. So there you have it. From a puddle that mysteriously vanishes to why it's hard to cook on a mountain, it all comes back to that same thing, the invisible glue between molecules. These tiny, tiny forces are shaping our world in these huge, profound ways that we barely ever notice. And it really makes you wonder, doesn't it? What other invisible rules are out there, quietly shaping our entire reality?